Welcome to the lecture Digital 3D Documentations in Archaeology. In this lecture, we want to talk about the important part, georeferencing and scaling of 3D models. Here, we see an overview of the topics we want to discuss in this lecture. This should help us later to find the individual topics more quickly. Let's start with the following question. Why is georeferencing an important step in 3D model creation process? So far, our work has focused on the planning and creation of 3D models of archaeological sites and artifacts via photo and video-based documentation. Georeferencing links these 3D models to geographical coordinates and anchors this data to the world. This can be of great and decisive added value for archaeological documentation. Fixed features should always be georeferenced wherever possible, as this provides concrete information about positions, orientations, and relationships to one another. Archaeological documentations are independent of time and can also bring together findings from campaigns that took place decades apart. Georeferencing simplifies spatial analyses and enables data to be brought together locally. Georeferencing also often plays an important role when it comes to protecting the cultural heritage of archaeological sites. For example, georeferenced models can be used to illustrate changes in archaeological sites or artifacts over time, which helps in the planning of protective measures. The following section is intended to provide a practical but compact overview of the topic of georeferencing 3D models. It does not replace the classic textbooks from the field of surveying. So let's start with the topics of geodesy and reference systems. Geodesy is a scientific discipline that deals with the measurement, representation, and cartography of the Earth's surface. Since the Earth is not shaped like a sphere, but more like an ellipsoid with irregular depressions and bulges, a model description is not quite so simple here, as you can see in the video. So-called reference systems, also called the geodetic datum, are used to determine the position on Earth. The aim of a reference system is to be able to clearly describe every point on the Earth in terms of position and altitude. A very well-known geodetic reference system is the World Geodetic System of 1984, which is used, for example, as the basis for the Global Positioning System or GPS. Essentially, georeferencing refers to the process of linking 3D models with geographical coordinates and embedding them in a global geodetic reference system. Georeferencing places the 3D models in a geographical context, making them usable for spatial analysis, map production, and other geo-based applications. Georeferenced 3D models can be integrated into a geographic information system, for example, in order to carry out complex spatial analyses and create comprehensive maps and digital terrain models. First of all, we differentiate here between geographic and projected coordinate reference systems. There are various coordinate reference systems that can now be derived from the reference systems. Classically, these can be divided into geographical coordinate reference systems and projected coordinate systems. A geographic coordinate reference system, or GCS, uses geographic coordinates with latitude and longitude to represent points on the curved surface of the Earth. Geographical coordinate reference systems are generally based on a mathematical model of the Earth as a rotational ellipsoid or geoid, as can be seen below left. In comparison, a projected coordinate system uses a Cartesian coordinate system created by mathematical transformations based on a geographic coordinate system. It projects the curved surface of the Earth onto a flat plane, creating a two-dimensional representation of the Earth's surface. These transformations are called cart projections and are used to minimize distortions and deformations of the surface. With the Geographical Coordinate Reference System WGS84 and the Projected Universal Transverse Mercator or UTM coordinate system, we have two very frequently encountered systems of both variants in the context of archaeological surveys. On the left, we see the Geographical Coordinate System WGS84, which divides the Earth's surface into degrees of latitude and longitude. Below this is the rotational ellipsoid, which forms the underlying mathematical model of the Earth in WGS84. This global coordinate system is used, for example, in GPS. At the top right, we see the projected coordinate reference system UTM and the division of the Earth's surface into 60 zones with a section on Europe and Germany. The geographical coordinate reference system WGS84 mainly uses latitude and longitude and sometimes also altitude values to indicate a position on the Earth's surface. Lines of latitude run parallel to the equator and divide the Earth into 180 equally wide sections from north to south. In the northern hemisphere, the lines of latitude run from 0 degrees at the equator to 90 degrees at the North Pole, and in the southern hemisphere from 0 degrees at the equator to -90 degrees at the South Pole. On Earth, the distance between 2 degrees of latitude is exactly 60 nautical miles, which is the equivalent of 111.12 kilometers. Let's take the Victory Column in Berlin as a historical landmark. If we look at its position, it is closer to latitude 53 than to latitude 52. We then write 53 degrees north, or N53 for short. The prime meridian for longitude runs from the North Pole to the South Pole through Greenwich in England. In an easterly direction, the lines of longitude run from 0 degrees on the prime meridian to 180 degrees on the back of the Earth, and correspondingly from 0 degrees on the prime meridian to -180 degrees in a westerly direction. In contrast to the lines of latitude, the lines of longitude run perpendicular to the equator at a distance of 60 nautical miles, but converge to a point at the poles. Now we can complete the example of the Victory Column with the nearest longitude 13, and then write N53, E13 for short. However, these two entries are very rough and are approximately 59 kilometers away from the Victory Column in Berlin. We obtain greater precision by dividing the coordinates into minutes and seconds. A degree is divided into minutes and seconds so that the large grid can be used in practice. 1 degree corresponds to 60 minutes with 60 seconds each. 1 second of latitude or longitude corresponds to a distance of 30.87624 meters. The center of the Victory Column is located with precise description approximately at the coordinates north 52 degrees 30 minutes, 52.1424 seconds, east 13 degrees 21 minutes, 0.4572 seconds. Alternatively, we can also specify the minutes and seconds in decimal notation. For example, the Victory Column in Berlin is then located at latitude 52.514484 and longitude 13.350127. The UTM coordinate system is a projected coordinate system and divides the Earth's surface into 60 zones, with each zone having its own Cartesian coordinate base. Each zone covers a longitude range of 6 degrees. These zones are numbered from 1 to 60 and cover the entire longitude range from -180 degrees to 180 degrees. In 2017, the UTM coordinate system ETRS-89 was established as a uniform spatial reference system for the cross-border use of geodata in Germany and Europe, and is therefore to be used as standard. Within each zone, the transverse Mercator projection is used to project the curved surface of the Earth onto a flat map. This projection thus flattens the geographic coordinates and minimizes distortions and deformations in the zone, making accurate measurements and calculations possible. Each zone has its own Cartesian coordinate base, which is given in meters. Nevertheless, this projection variant is not without distortions, which makes location-dependent correction factors necessary. The baseline of the zone that intersects the equator is referred to as the false easting and has a longitude of 500,000 meters. This serves to avoid negative coordinate values. The reference point for the height, here the y-coordinate, is the equator itself. The UTM coordinates consist of an x-coordinate, here easting, and a y-coordinate, here northing. The x-coordinate is given as the distance in meters from the false easting baseline, while the y-coordinate gives the distance in meters from the equator. This means that we always get positive values for the x-coordinate in relation to the false easting, while positive values for the y-coordinate are only found north of the equator. If we stay with the example of the Victory column in Berlin, the UTM coordinates in zone 33U are Lang x and y coordinates, as you can read there. We then write in a shorter term, which is already presented. It is often used for small-scale surveys and is therefore suitable for most archaeological 3D documentation. But we still have to answer an important question here. What about the numerous reference systems used by archaeologists in the past? As a representative of numerous other reference systems that were used in the past and whose data was used in archaeological documentation, we will take a brief look at the Gauss-Krüger system that is frequently used in Germany. What is important here is how we can deal with the data in the future and transform it into the currently used UTM coordinate system. Similar to the UTM coordinate system, the Gauss-Krüger system divides the Earth's surface into zones. The division into zones can vary from country to country. Each zone has a specific longitude range. A curvature calculation is carried out for each zone in order to take into account the distortions of the Earth's curvature. A meridian strip is defined within each zone, which serves as a reference meridian. This meridian has a longitude of 0 degrees and is used as the 0 point for the x-coordinate. On the left, we see the Gauss-Krüger coordinate system. Below, we see 3 examples of coordinates in Gauss-Krüger with values for x, y, and z respectively. On the right, the coordinates can be quickly converted from one reference system to the other using one of the numerous online platforms. In this example, the first point was entered and automatically converted to UTM or WGS84 coordinates. Now let's take a look at which georeferencing strategies are available. The use of a Global Navigation Satellite System, or GNSS, is a common method for recording the geographical position during a photo shoot, for example with a multicopter. The well-known global GPS is often used for this purpose. On the left, we see an example of a photo from a documentation campaign in the Orkhon Valley in Mongolia from 2018, which was given a GPS position in the EXIF data when it was taken by the multicopter. In the middle, if we look at the properties of the photo in the Windows operating system, for example, we can see the saved GPS data. On the right, the coordinates can be easily displayed in the Google Earth map material and thus localize the photo. Here we can also deduce the orientation of the photo from the map material. The satellite signals contain precise timestamps and position data that are used by the GNSS receivers to calculate the distance to the satellites. By calculating the distances to several satellites and using triangulation methods, a GNSS receiver can determine its exact position, speed, and altitude. A global navigation satellite system uses the constellation of currently available satellites to determine position, navigation, and time measurement. GPS in United States of America, GLONASS in Russian Federation, Galileo in European Union, and Beidou in People's Republic of China can be summarized under the collective term GNSS. The quality of the GNSS signals, the existing environmental situation, and the number of visible satellites have a direct influence on the precision of the positioning. At this point, it must be mentioned that relying on unchecked GNSS data can lead to very erroneous data. Here, an analysis of the environmental situation with the recording of test data should provide certainty. In a later lecture, we will talk about the localization of underwater systems. Here we see a raft variant as a preliminary stage to the wireless solution as a recording system that was used in 2017 at the Pile Dwelling Station at Lake Mondsee in Austria. On the left, we see the raft variant used with various cameras and diving lamps on a boom for data recording. A GPS receiver is mounted on the head of the UUV, which enables positioning within the navigation software. In the center, we see the navigation software. This is where the project, the area to be recorded, and the recording trips are managed in real time. On the right, we see the results of the GPS tracks of various dives in different colors. While the first dive still shows little deviation between the real position and the GPS position in green, the tracks lose their reliability over time. The GPS position was sometimes more than 50 meters away from the real position. Although the water surface was calm, the GPS errors are due to the location in a valley and the reflections on the water surface. But we would like to make one more point here. By combining GPS GNSS data with the photos, 3D models can be transformed into the desired geographic coordinate system. This method is particularly suitable for large-scale outdoor surveying projects where high spatial accuracy is required. The signals from the satellites can be strongly influenced by reflections and occlusions in the surroundings. In order to significantly increase the precision of the positioning and thus the photos taken by multicopters, systems with so-called real-time kinematics, or RTK for short, can be used. An RTK system has a base station in addition to the mobile receiver, here a multicopter, which can be seen on the left. The base station receives signals from the satellites and records the phase differences between the received signals and the known coordinates. This generates so-called differential correction data, while the multicopter receives the correction data from the base station and uses it to precisely calculate its position. The DJI Phantom 4 is also available as an RTK version, as shown on the right. In combination with a base station, high-precision georeference terrain models can be created without having to place and measure additional control points. Below right, we see an RTK system in use. The correction data is transmitted from the base to the remote control and from there to the copter. Ground control points are known reference points in the real world that contribute to the precision of georeferencing. By defining control points in the images and their corresponding geographical coordinates, accuracy improvements and error corrections can be made. The number and distribution of control points have a direct influence on the quality of georeferencing. In terrestrial surveying, ground measurements are usually carried out using total stations or GNSS instruments to record control points and geodetic reference points. These points are then correlated with the images to perform georeferencing. This method offers high accuracy and is well suited for small to medium-sized projects where precise spatial referencing is required. The positioning of control points is an important factor in the georeferencing of 3D models in the field. The study by Sanz Ablanedo and other confirmed other studies and showed that optimal accuracy is achieved when the GCPs are evenly distributed over the entire area. Ideally, the GCPs should be distributed in a triangular grid of nodes, as this distribution minimizes the maximum distance of any point to the nearest GCP. The authors also state that it is not possible to correctly evaluate the geometric quality of a 3D photogrammetric model with only a few control points and suggest more than 3 GCPs per 100 photos as a rule. However, this also depends on the number of pixels and the quality of the camera. At least 3 control points per 100 photos should be evenly distributed across the terrain, ideally in a triangular grid of nodes. Pix4D suggests a number of 5 to 10 control points. Actually, only 3 control points are required for georeferencing, which cover as large a triangular area as possible. However, a larger number makes it possible to determine the so-called root mean square error via the available control points and thus provide an overall statement of the model quality. Another method is to use local reference points, so-called natural markers, that are available in the vicinity of the area to be georeferenced. These can be prominent terrain features, building corners, or other easily recognizable points. Georeferencing can be achieved by measuring the geographical coordinates of these reference points and correlating them with the images. However, there is a risk that these natural markers may not be found later or may even be incorrectly assigned. Let's now take a look at a few examples of georeferencing. Let's start with an example, a large sacrificial stele from Tamtoc in Mexico, for which no georeference control points are available. The location is not decisive here either, but the scaling of the find for further investigations is. Before the photographs were taken, various measurements were taken with a measuring tape, see top left. A multicopter system was then used to record videos of what can be seen below and later reconstructed videogrammetrically into a 3D model in reality capture. The results can be seen on the right. The reality capture software now makes it very easy to place control points in the 3D model and then verify or correct them in the photos. After 2 points have been placed, a distance between the points can be defined via distance measure, in this case 5.8 meters. The model must then be recalculated so that all distances are readjusted based on the distance measure in the model. We can then check whether the defined distance measure now corresponds exactly to the input and take further measurements in the same way. In the following example, we will look at a large-scale documentation campaign in which many square kilometers of the Mongolian steppe were recorded and reconstructed with multicopters in 2018. It was not possible to place control points in front of the images due to the size of the documentation area and the short time planned for the documentation. The individual recordings were planned with the Pix4D capture software and carried out with 2 DJI Phantom 4 multicopters flying in parallel. Systematic flight planning, based on a quadratic flight mission, was planned and tested in advance and adapted and adjusted to the altitude of the Orkhon Valley at over 1,500 meters in Mongolia. A flight mission has an expected, defensively calculated flight time of approximately 12 minutes and ideally provides a ground resolution of 2.73 centimeter per pixel. With 4 missions, each of which can be completed by 2 multicopters in parallel in 2 flights, more than 1.1 square kilometer can be covered in 30 minutes. The numerous photos were processed in packages using the Drone Deploy web service. This had the advantage that the data could already be sent from the yurt in the Orkhon Valley and processed virtually on-site without a great deal of computer effort. The individual images with the stored geotags from 4 flight missions are already well displayed in the context of satellite images when the data is uploaded, as can be seen at the bottom left. Next to it is the result of the resulting orthophoto. The project focused on significantly expanding the data map already produced by a LiDAR documentation campaign in 2007. We can see this on the top right. The interaction of different image variants in the same reference system can be seen very clearly here. Existing but incomplete structures could be seamlessly expanded and new ones identified. This is one of the great advantages of georeferencing. In this context, however, it must be mentioned that the planned ground resolution can only be achieved with an absolutely flat terrain. Due to the large number of flights, the overlap of the trajectories was very tight at 70%. However, the Orkhon Valley also has very hilly parts, which had to be taken into account for each flight mission with a possibly adjusted starting point, which can be seen at the bottom right. Let's now take a look at a classic reconstruction example in which control points, in this case color markings, are recognizable in the photographic material and are available as coordinates. This example of a transept of Plauen Castle, or also known as Castle of the Reeves, in Plauen in Germany, was photographed in close cooperation with the State Office for Archaeology of Saxony, or LFA, in September 2014, using a DJI Phantom 2 and a GoPro Hero 3. At the top left, we see the sketch of the transept with the positions of the survey points provided by the LFA. As is the case in most regional projects before 2017, the 10 survey points are available as Gauss-Krüger coordinates in a text file. Below we see the original coordinates in the Gauss-Krüger reference system, and next to them the result of the transformation into UTM coordinates. The elevation values were converted from the DHHN92 elevation system to the currently valid DHHN 2016. The survey data can now be imported into the reconstruction project. At the top right, we see the linking of the control points with the 3D model, and the verification or correction within the photo data. To the right, we see the management of the control points. The georeferenced 3D model with the control points can be seen at the bottom. The georeferenced 3D model can now be used not only to derive distances, areas, and volumes, but also to determine the corresponding world coordinates for each point. The resulting orthophoto of the transept in Plauen can be seen on the left. After successful georeferencing using the existing coordinates of the control points, reality capture can already be used to take a wide range of measurements. For example, we can mark areas and thus automatically obtain the size of the areas. As can be seen on the right, we can also simply use distances between any points to take a measurement in the orthophoto. However, these measurements are not limited to the orthophoto. Once the 3D model has been georeferenced, distances, areas, and even volumes can be measured. Many of the programs used for photo-based 3D reconstruction also offer the possibility to perform precise measurements in the resulting output. In the first lecture, we have already gained an insight into the use of drone deploy for visualization in false color representation and for measurements. In the associated practical exercises, we used Visual SFM for initial reconstruction experiments. Visual SFM can also be used to georeference 3D models and carry out measurements in them. Later, we got to know the commercial program Reality Capture, which provides comprehensive processing and evaluation functions. In the following section, we will get to know another example, WebODM, a variant of Open Drone Map. The open source project Open Drone Map is slowly becoming a good alternative to the commercial version of Drone Deploy. Although the processing speed is still much slower in comparison, some of the results produced are already at the same level. With the WebODM web interface, the developers offer a user-friendly solution that can either be installed by the user or is available as an installer for a one-off fee. At the top left, we see a prepared image folder with images from the 2018 Mongolia campaign showing a structure in the surrounding mountains of the Orkhon Valley. We create a new project in WebODM and link the images to it. Now we can select numerous tasks for processing and make settings. Once the selection has been made and the processing has been checked, the process can begin. The images are first uploaded and then processed. Processing these 245 images with the desired results and settings, for example, took almost 14 hours. The results are then available in the WebODM user interface for further analysis and evaluation. WebODM offers two views for measurement. In the 2D view, the georeference orthophoto can be anchored in Google Maps and, depending on the opacity selected, can be displayed. In the icon menu on the right-hand side, you can select the point called Measure Volume, Area, and Lengths. In this way, we can quickly measure distances in the georeferenced orthophoto. Let's take a closer look at the image. Above, after processing, the result of the georeferenced orthophoto can be viewed in the map material of Google Maps. Here we can overlay the model accordingly by selecting the opacity. To the right, we can see an example of a distance measurement on the central structure. Below, if we switch to the 3D view, the model is displayed in the portrait viewer. On the left, we see the 3D model with the calculated camera positions and orientations. We can see here that a faulty connection component has been created in the model above the structure. To the right, we can see that navigation in the 3D model allows, among other things, zooming in and adjusting the camera orientation. On the right, we see three measurement examples. Distance measurements can be carried out in all directions. Below, we see a volume determination of the central structure. In addition to the option of determining angles, on the right, we also see the option of determining the angle in relation to the north direction. In this case, we see a perfect north axis in the model and a symmetrical structure based on a circle with perfect corner points at every eighth. After listening carefully to this lecture, answering the following comprehension question should help you to summarize the most important statements again on your own. The practical part is about finding and transforming a coordinate pair. We will then get to know the WebODM software with an example.